Hello. Hello. Good afternoon. Good afternoon. Thank you. And good morning. Okay. Good afternoon, Justin. Good morning, Jenna. Good afternoon, Alyssa. Good afternoon, Rachel. Hello, Wenyi. Good afternoon, Kimberly. Good morning, Sarah. Good good heavens. Okay. Good. Hello, Alea. Hello, Amber. Hello. Oh, here we go. Hello. Good afternoon, Erica. Good afternoon, Abby. Good afternoon, Eileen. Thanks. And someone else just. Oops, sorry. How? Wait, there's someone else. Where is it? Oh, yes. Hello, hello. Okay. So I want to. So I owe you some things now. Let's get right. So first of all, I am aware that if you turned in anything at all in the last like couple of days, then you have not gotten it back. I mean, you shouldn't have. I have not done it yet, and it's not personal, and I apologize. And I have not yet updated. We spent last Monday sort of finding an issue with the solutions and redoing certain things from scratch. And I do still intend to update the old solutions so that everything is consistent, but I have not done that yet, so I apologize. So you're still working with those solutions. And the one thing that you had never gotten from the old solutions, although you may have accidentally gotten some of this, we've never talked about problem 3. We also may not have talked very much about problem 2, but I think and I can still happily answer questions about that. I can even give hints and stuff, but I think there, look in the solutions. I don't think there are errors. Um, some things that you might not have figured out on your own, you can see there. But I really think it's incumbent upon me to talk about problem 3 today, because that would seem like the most intimidating and most new thing, and it kind of is. And it's as hard as it gets on this exam. So right. So I will still answer questions and stuff like that, but I kind of want to hop straight to problem 3, unless there are glaring issues. And I'm reminding myself too. We said, is it? What did we say? I know we posted it, but am I posting the exam this Friday at 8? Did we say? Oh yes. Oh wait. Oh sorry. Oh hold on. Let me look in the chat. Oh okay. Hold on. I'm open also. Oh wait. There's a very good. Okay, this Friday. Okay, thank you. Okay, sorry to hear that, but okay. Yeah, so I definitely want to do this problem 3 today. Okay, but there's a question in the direct chat that seems very worth answering. So I'm not going to say the person, but if I'm understanding, so okay, I had a question about problem number 2. In that question, when I asked for angular frequency, I took the square root of the pi squared over 16, which is right, I did. So problem 2 now to everybody. A quick question about problem 2. At the beginning, I did take the square root of pi squared over 16, because that was the differential equation. I took the square root of that and said, that's the angular frequency. Right. Did that in the solutions. But in the first question, B and C, when we solve for period, were we supposed to take the square root of KQ over RQ? No. Sorry, let me read this out loud. In the first question, number B and C, when we solve for the period, are we supposed to take the square root of KQ over R cubed? The KQ over R cubed stuff only applies for the first few pages of the exam. Like that was a math thing. KQ over R cubed cannot help you at all, any of you, for the pendulum. The way to get the period for the pendulum in the pendulum is you take the angular frequency that you got in part B and flip that, divide that by 2 pi and flip that to get the period. The KQ over R cubed should be thrown away after the first problem, if that helps. I'm not sure. And whoever's asking the project can ask more if they want. And again, I can take questions about problem 2, especially if they're concrete and straightforward like that one is. I can take them. I think I should spend the bulk of my time today on problem 3. So that's where I'm about to go. Okay. All right. Oh, and again, so here I may have posted by accident, I might have given you a document that had a partial solution of it. In fact, maybe I should. Well, it doesn't matter. Actually, yeah, I am going to. Hold on, I'm going to turn to a different document for this, whether you have it or not. So bear with me for a second. Right. Okay. Okay. So we're going to look at problem 3 of the midterm exam, of the pre-midterm exam. If whether you've turned to it yet or not, there's some things about it that look intimidating at first, without a doubt. One thing is that right away, we are introducing a new equation that you may remember from physics 1, or you remember vaguely, or whatever. And we're just introducing it here, or reminding you of it. And we're going to start using it right here, right now. In this pre-exam, the equation I'm talking about that's just being introduced here, and I'll turn back a page, is this. Okay. Now it has vector symbols in it and stuff, and we don't have to get intimidated by, we don't have to worry too much about the vector symbols for the moment, if you don't like them. But the thing about this equation, and you can even pause, you can even not worry about the negative sign for a moment if you like. What this equation is, and I'll write it again in another way. Like this. Okay. Why? Okay. What we're saying here, whether you do have noticed this from physics 1 or high school, or it's totally fresh to you, what we're saying is F net still equals ma always. The sum of all the forces on an object always accelerates that object at a rate directly proportional to the sum of the forces. There's different kind of forces that can act on objects, right? And one that we deal with all the time is gravity. The actual way that gravity works, like gravity, we frequently treat gravity as the attraction of objects to the center of planet Earth. We wonder for a while, why does Earth have this special property of pulling everything down towards its center? And it turns out that wondering why Earth has this special property of pulling things down toward its center, wondering why Earth has that special property turns out to be much like wondering why Earth has the special property of sitting still at the center of the whole universe while everything goes around it. And the answer to both questions is it has that special, the answer to why it has that special property is that it doesn't. It's not special, right? The Earth does not actually sit at the center of the universe while everything goes around it. It's just a rock flying through space like any other rock in space. And similarly, Earth doesn't have the special property of pulling everything toward it at some rate mg. It's that everything in the universe, it turns out, every point of mass, every bit of mass, every particle, every Euclidean infinitesimal volume of mass, pulls on every other particle of mass in the universe with a certain automatic force, a certain number of newtons that is occurring just by virtue of existence, of mass's existence. Meaning that, and I'm going to look in the chat in a second. I see there are things happening in the chat. I will look in 1 second. But to this here, what I'm writing right here is called second. This is called Newton's universal law of gravitation, meaning it's the recognition that this gravitational attraction of one body to another, this pull that seems to occur through empty space, like without any touching or any activity or any special initiation or attempt to do this. Apparently, when any one bit of mass sits anywhere in space, it automatically pulls on any and every other bit of mass sitting anywhere else in space. It automatically exerts a pull on the other mass. And by Newton's third law, then the other mass automatically exerts a pull on it, just automatically for existing. And we call this gravitation. Like as long as you are a mass, evidently you automatically pull on all other masses. Now, different masses pull on each other by different amounts. The amount that we pull, like the amount of strength of attraction between any two objects, evidently is directly proportional to how massive each object is. Okay, that sort of makes sense, right? That's why M1 is multiplied by M2 in the numerator of this fraction. Like if you're given two, so M1 and M2 are point masses. They are particles of mass. They could be very different in the number of kilograms that they each comprise, but they're both indistinguishable when it comes to volume. They're both like Euclidean points of mass, of arbitrary amounts. The bigger either one of them is, the more they'll each pull on each other. And the closer to each other they are, represented by R, the displacement between the two, the closer they are, the more that they will pull on each other, such that the square of R is in the denominator. And the magnitude of gravitational force exerted by one arbitrary object on another is inversely proportional to the square of the distance between the two objects. And that all seems like why is that? We're going to actually discover why in this class. We are going to find out why. But apparently at first, our view of this is the same as Newton's view, which is just that this seems to be true. It's not clear why at first. It just seems to be from the data true. This is a double equal sign equation, not a triple equal sign equation. So I'm positing now. I'm saying this in the context of this midterm or whatever. There is a force that any and every given mass point in the universe exerts on every single other mass point in the universe, and we call that force gravity. And its precise strength in newtons is determined by this combination of constants and variables. And in all of this, what is capital G? Capital G is just a big proportionality constant. And it's not necessary at all if we it's not necessary at all unless we insist on keeping everything in metric units and make sure that our force, expression turns out being measured in newtons. Well, I'll just, G is G is the universal gravitational constant. You certainly do not have to memorize it. Any context in which we use it, it's always the same. It's always a given. I mean, I do happen to know it at this point. What you need to know about it is it's a very teeny, tiny number. So it takes a lot of kilograms located at a fairly close distance in order to generate a force that's really huge in newtons. Like gravitational force that exists between random objects is very, very tiny. And it usually takes like planet-sized objects to start actually exerting gravitational forces that really are measurable or matter in comparison to others. Okay, and that's all. So partly G happens to be a really small number. The gravitational force that exists among objects is not intrinsically very strong. But the other thing about this constant proportionality is it has units, newtons meters squared over kilograms squared. Not a coincidence. That's actually all that it's about. It's just a number that ensures that we could cancel out the meters squared from the denominator of this fraction with the kilograms squared in the numerator of this fraction. We could cancel them out and be left with newtons as a force should be. So there's nothing magical about this constant. It's just like a conversion number that makes sure the units work out. Why do I care about all of this? And why am I suddenly asking you to care? Very fair question. I'll show you why. wait, what that is, and again, supposedly that's like something we see in physics one, but depends who you had for a professor and what kind of semester it was and whether we're in quarantine. So I don't know. But this is, I mean, there's Newton's 3 laws of motion, and then there's this Newton's law of universal gravitation, which tells us precisely how strong one point of mass, one particle, would ever pull on some other particle of mass. Now, what do we actually do with this law, or how do we apply it to anything larger than a point? Like, you hear people talk about gravity in the context of planets and stars and moons all the time. That is where it comes up. But how precisely do we apply this law of gravity to large objects, large collections of points, such as planets and stuff? Most specifically, like this question is asking us to analyze how gravity would work if you had a huge solid sphere of total mass and uniform density. Okay, so now I'm going to start getting into the problem here. What's given? All right, so what's given so far? What's given is that we have this law of gravity that tells you how hard one point of mass pulls on another point of mass. That's a force that gets plugged into F net equals ma like any other force, like Hooke's law of force or friction force. It's a force that, and you know it as a force of gravity. We're just now applying it to the universe, not just to the surface of the earth. What we're being asked to consider now in this problem is, what if we had a solid sphere of mass, like not just one dot, but an actual big ball of mass, like a planet or something, or a moon, right? And let's be specific, like a ball of total mass, capital M. So that's what I'm writing. That's what I'm writing. Sorry, here. A mass of total mass, capital M, a radius of capital R, like given constant radius. Like this is a ball that we're picturing, and it's like a solid ball. So I do that stupid like shadowy effect that I don't do it. And now I'm introducing a piece of notation right here, right now. I mean, or in the practice exam, I'm saying, or have we introduced before? Yeah, right, I'm introducing this lowercase rho right here. That's a lowercase Greek letter rho. What it's going to be defined as from now on is three-dimensional mass density. Let me be more specific. Here, I can, this will make it slightly bigger. Okay, say that funny V stands for volume, all right? Then okay, I'm going to use the lowercase Greek letter rho to stand for, in effect, density. Like you say in chemistry, density equals mass per volume. Okay, that is what I'm talking about here. Rho is going to stand for density, like mass per volume. But I have to be a little bit more specific now because I'm a physics guy, and I believe like a lot of like density means, what density really is how closely packed together things are. Density is like stuff per unit space. Now in chemistry, generally what you're dealing with is a three-dimensional space, and you're generally dealing with mass. So you say like mass per volume is what density is. I just want to side note here, in physics, sometimes we're dealing with three-dimensional spaces, sometimes with two-dimensional spaces, sometimes with one-dimensional spaces. Whenever we talk about unit mass per unit volume, we're going to call that three-dimensional density because it's mass per volume, volume's three-dimensional. And we're going to designate that with the symbol rho in physics. And what I'm specifying here for the problem, why am I even saying all that? I'm going to say, let's imagine here that we have a case where rho equals rho naught. What? Like what? Rho equals rho naught. What's all this? If rho stands for density, and we always have in physics that something naught means the value of it at the beginning, right? Like X naught is the very first value of X, or V naught is the very first value of V. rho naught would be like the very first value of rho, like where you first measure the density. If I write that density, if I say from here on in this class, if I say something like this, right, that means that that variable, which in this case is a constant, right? It's like when we say a equals a naught, that means acceleration is a constant. If we say a equals a naught, that means the value of a at any moment is the same as what it was at the beginning. That's a shorthand for saying a is constant. Just reminding you, that's what I'm doing here. Like all this, so I'm not trying, I know there's a lot all of a sudden going on with notation. All of a sudden it feels like you're learning something, which is like weird, right? But it's actually just notation. I'm saying here, we're going to picture a ball. All I'm really saying is picture a solid ball, but picture it's like really solid. It's actually solid, like the same solidity throughout. Like every chunk of volume that you pick has an equal chunk of mass in it. It doesn't get like thicker and then thin or something. It's just like equal thickness throughout. That's what I'm saying here. The density is a constant. The density is uniform. The ratio of you can take the smallest amount of volume over here and you'll get a certain amount of mass. I don't care if you go to the infinitesimal level, it's never going to change. That's what we're saying. Okay. So we've got a ball, uniformly dense ball of mass. What our question here, having just introduced gravity as an idea, we're now going to ask, okay, what if you're somewhere in that ball? Like if you're somewhere in that ball, so if that whole ball, it might be a planet, it might be a moon, it might be a star, but it's this big uniformly dense, solid ball of mass capital M1. If you're somewhere in that ball at some random independently variable location, lowercase r, right? So I'm looking over here now. I'm saying lowercase r stands for where some little particle might be sitting that we're interested in, or you might be sitting. It's variable. It's like the position, the displacement from center that we're testing as an independent variable, as opposed to capital R, which is the constant given radius of the whole ball, right? We're somewhere in that ball. And what we want to know is how hard is everything pulling on us? Like in what direction? Like there's a bit of mass over here, it's pulling us toward it, right? There's a bit of mass over there because we're in the middle of this, pulling us toward it. There's a bit over here. What's the sum total effect of all? In other words, what's the gravitational effect of something if you're inside it? That's what I want to know. It seems like an out of nowhere question. I know. You'll see why by the end, why it's actually part of this exam, part of this topic. Remember, okay. Right. Yes. Private chat thing that I can't see. Yes. Cool. Sorry. Right. Yeah. No. I'm that ADHD guy. Right? How many light bulbs does it take to change me? I'm saying to everybody, and this seems like a very weird question. I know, and it is even weirder maybe but this is why we do exams the way we do them. But please bear with me with this question, because remember, the secret agenda of this whole exam and the whole topic and everything is this whole idea of harmonic oscillators live where you don't see them. We're trying to get inside the math of harmonic oscillators so that we can recognize and find harmonic oscillators even in places that don't physically look like them. We're trying to find springy phenomena even where we don't see metal springs, like we found it in a weather phenomenon on homework 3, and we found it in a pendulum, right? So just like this is going somewhere, obviously. It's not as unfair as it might seem. But anyway, so what I'm asking right now is, okay, if I know what one bit of mass does to another bit of mass, what if I'm surrounded by mass everywhere, a whole bunch of bits of mass everywhere around me? How would they all sum totally pull on? That's the question. Excuse me, someone's coming in. Hold on a second. That's the question. How could I possibly answer that based on what we said so far? Well, if we look at the law of gravity of GMM over R squared, the one I just introduced, it actually has a couple of implications. Now I can post a video about this too if you want. But okay, so sorry. So this is the question, first of all. I'm just rewriting here. The question is, if we're somewhere inside this plum pudding, so to speak, somewhere inside the solid sphere, what I'm looking for is, what is the net total? I should really say here, compute. What I'm really asking here is compute the sum of all the gravitational forces on me at some arbitrary location. Again, what do I mean all of the gravitation? I mean, what we know about gravity is how one point automatically pulls on another. Like why we're not practicing that gravity equation for 400 years before I even asked this problem is it is a plug, like at this point, I trust you guys as scientists. Like GMM over R squared is a plug-in. If you know the two masses and you know how far apart they are, you plug in the values, you multiply by 6.67 times 10 to the negative 11, and you get the force in newtons between two masses. Like we could practice that all day, but you're doing much harder stuff than that in this class already. So I'm saying I'm going to trust that we all trust each other, that given any one point of mass pulling on another, you know their two mass sizes, and you know how far apart they are, you know the newtons of pull between them. Now I'm saying, okay, fine. But what if you're immersed in all these points of mass? They're all around you. Can we say anything about that? What, like a little one pulls you from here, another one pulls you from here, they all add up. Can we say anything about how they all add up? Well, I'm going to say this. Oh, okay. Well, I said that, all right, this is the given, right? I'm just restating again the point. You could write this down or not. You could ask me to stay on this page or not, but I'm saying what's given is this law, GMM, and it's written in a vector way. You don't have to be intimidated by the vectors. You can ignore the vectors for the moment if you like, but they're just expressing that there's direction as well as magnitude. And the negative sign really shows that it's a pull. Yeah, the negative sign means it's a pull, but given that, okay, what I'm going to do is I'm going to say, all right, if I know how any two masses pull on each other, let me start. Well, I'm going to break this problem down. And again, there's a reason I'm asking it. It's another application of our topic. And we need this for the rest of the course too. It's not as arbitrary as I should stop talking about. Okay, so we're going to break this problem down. What we're asked is plum pudding, solid sphere. What I'm going to consider instead, to make the problem easier on myself, I'm going to do what Newton did. I'm going to start by just considering a shell of mass, radius capital R, right? So in other words, a ball, but that's hollowed out, empty space in the center. If I consider that, that's my M1. And then I consider some little particle and I ask, what's the relationship between that whole big thing and the particle? What I will find is the following. If I'm okay, so here's these drawings here that are on this page. Obviously, I'm going to give to you. These are meant to be shells now, spherical shells, spherical. Okay, if you consider the top drawing, this case is the case where lowercase r is greater than capital R. Meaning I've got this shell of mass, I'm somewhere outside it, okay? Well, if you take this idea to the limit, I'm going to argue this from different ways, but I'm just going to pause it right now, especially because we have an exam coming. I'm trying to keep things concrete, whatever. But I have a link to a video I can show you that expands this further, what I'm about to say, which is this. If you're far away, if you're outside that whole shell, if you're far away, as you get farther and farther away, that shell to you is more and more like a dot, like a circle, like that shell. When you're outside that circle, it's pulling on the whole. That circle from the outside is pulling everything in toward it, just like a point located at the center would, right? A circle, in other words, a circle is symmetric. A circle is a locus of points equidistant from a point. That circle, if you're outside it, that circle does not pull things to the left of it any more than to the right or above. It pulls on all the space symmetrically. So if you're outside it, you would get pulled toward that circle as though the whole circle were just one point of mass located on its center. In other words, the exact way that we treat Earth all the time. We always say we're being pulled toward the center of the Earth, and we know how far it is to the center of the Earth. We know how much mass there is in the Earth, so we always act like we're being pulled by this big M toward the center of it. In other words, we don't bother adding up all the constituent parts. We're just like this big ball that we're outside of is as though it's a big point located at its center. Every part of it that's not at its center, for every piece of Earth that's a little bit to the left of its center, there's an equal piece to the right of the center. And they're all pulling on us. So we say if we're outside a shell, if we're outside, then all the forces act just like gravity always does. Outside, I'm saying, if you, then this is important. I'm making a distinction here. Like, hopefully I'm saying everything I'm saying sort of does make sense. Like I'm saying it for the first time, but I'm well, sorry, weird things are happening. Sorry, my computer's doing weird things. I'm sorry. Hold on. I have no idea what. Okay. And it's not any of you. Oh, my computer's really doing weird things. Hold on. I'm sorry. Oh, okay. Okay. I'm saying, and please bear with me. This is a lot. It's hopefully what I'm saying is a lot of little things. Each little thing is hopefully okay. It's just a lot of them. So this hopefully okay thing that I'm saying right now, and we could is that if you're away from Earth, if you're outside, if you're away from any kind of shell like Earth, but like a hollowed out shell, if you were outside it, the whole thing will just act as though the whole thing, or the total mass will act as though all of that mass were concentrated right at the center. It's kind of like the old median mean idea where the thing in the middle represents the whole. If you're outside the shell, if you're inside the shell, so this is now case two I'm now looking at, okay? So I'm saying if you're outside the shell, a spherical shell of mass, the whole shell will act to you, will pull on you with the same force as one dot of equivalent mass would if located at its center, if you're outside. If you're inside the shell, okay, the shell now, I'm saying something. It's not the answer to our question yet, because our question in the exam, and believe me, everything I'm saying right now is also the hardest part. Once I get over this hump, then it will all be straightforward, I think. But what the exam is asking for is what would I experience if I were somewhere in the middle of plum pudding, like somewhere amidst a solid sphere? And in order to answer that sort of hard question, what I'm doing right now is I'm analyzing in my brain, I'm analyzing, well, what would happen, first of all, in a shell? Like that might be an easier step. So I'm saying if I were inside a shell, so that's this drawing here, case two. If I were, so the shell has a radius of given constant capital R. But if I happen to be at some location, lowercase r, if my displacement from the center is somewhere, and I'm this little particle m2, and I'm there, what I'm going to assert to you all now, and this is I'm possibly surprising, but possibly not. I'm going to say if I'm right there, somewhere in that shell, so everywhere around it is space, it's like a vacuum, but then there's this shell of mass around it. The total net gravitational effect on me right there inside a shell is zero. I'm not saying that's obvious. I'm also not saying it's a shock. Like to some of you, it might seem obvious. To others of you, it might seem like, what? I honestly don't even know what my opinion on this at this point. I'm just saying it's true for starters. Okay. If you can make sense of it, great. If you don't think it makes sense, you're not crazy. That's why it's worth saying. But I'm saying if you're outside a shell of mass, a spherical shell. Surprisingly or not, the whole spherical shell will basically act as though it just were one point. And the one way to see that in your mind is go really far away from it in your mind. Like if you get really far away from the sun, it looks to you like the sun is just a point, right? And then we're saying like, yeah, that's not crazy. But now I'm saying if you're inside a shell, you're automatically weightless. I'm saying your gravitational force on you is nothing. Like G, the value of 9.8 that you experience when you walk around the surface of the earth, if you're inside a shell, it's zero. Now, that is what I'm saying, and we're going to use this. And I'm saying it for the first time, and I know it, and I see the time. But like, I think it's important for me to take a moment to kind of suggest to you why I'm saying that. So, okay, so I'm going to pause for a sec. So I'm about to expand on this second case here. I'm saying, and I believe this does follow from the logic of gravity and the nature of space and time, but it follows. So I think I can show it, but that doesn't mean it's obvious or that we should have just seen this right away. It is like a Newtonian, it's like a Newton thought process. And again, I can give you full expansion on this in a video. Like, but I'm saying this. Okay, I'm just saying this is the question I'm about. I'm totally not asking you guys this. I mean, actually, that would be an unfair question. I'm saying this is the question I'm about to answer. Like, this is a rhetorical question. I want to stop and so I'm asserting that within a spherical shell, spherical, like spherically symmetric, like again, uniformly dense, like no tricks. I mean, this is hard enough, but inside a shell, anywhere you are inside the shell, I'm claiming all the whole gravitational effect of the whole shell. And there is one, like each little bit of the shell does exert gravity, like on the whole universe. But I'm saying if you're anywhere within that shell, it's all going to cancel out to zero and you'll be pulled nowhere. And I want to explain why. Now, first of all, so that's what I'm about to explain. But first of all, so yes, that was nice. Okay. Remember, the shell is of radius capital R. You are at some random location, lowercase r. Now, one thing is, if r is 0, I think it's clear. If r is 0, then like this side is pulling you that way, and that side is pulling you that way, and that side is pulling you. I hope it's clear that if you're literally at the dead center, you're being pulled every way, a lot, but every way equally, so they would all cancel out and be nothing. What I'm arguing is even if you're not at the center, something like that happens. Okay, I'm saying if you're right here, okay, you're this little particle there at the red dot, like you're M2, this little particle at this random location inside this shell. This is, again, a shell. You're at this random point, the red point, M2. Now there's a chunk across from you, let's call it MA, a big mass chunk. And what it is, it's like a two-dimensional, it's like a sector of the circle, but two-dimensional. It's like a surface area region, if you, right? I mean, I can't draw 3 dimensions, but there's this slab there of the shell called MA, and it's pulling you toward it by virtue of gravity. Right? Gravity between it, MA, and you, M2, right? And it's pulling you toward it. So you would think, okay, you fly toward it. There, but for any chunk that you find MA, there is a chunk on the other side called MB. Look at the way I've drawn it. And this chunk on the other side is bigger, right? Bigger. So it's going to pull harder for that in that way, because GMM over R squared, but it's also farther away. So it's going to pull weaker. So the question is, which of those two effects like dominates? Like there's another chunk on the other side of you that might be pulling harder or less hard, or maybe equally as hard as the one across from you. And my ultimate argument is it's equally as hard because of, yes, exactly what Andre says. I'm saying ultimately that the effects of these two things cancel out because remember, like if density is uniform, right? If this whole shell is not, it's not a trick, it's like the same thickness over here as it is over there, then everywhere, like just call that thickness 1 or whatever, then right? For any two equally sized regions of volume you pick, the corresponding masses will be the same, or vice versa. You want to know how much more massive one chunk is compared to another. Well, compare the volume of one to the other because the mass per volume ratio is the same. Now, volume is 3 dimensions. The thickness is the same all the way around. So these two things are not going to be different because of thickness. Their thickness is the same. They're going to be different because of surface area, right? Oops, sorry. Since density is a constant, okay, almost done making this point. I mean, it's getting very Englishy, but I'm saying, right? So there's one mass pulling on us, and then there's a mass on the other side pulling on us as well. I mean, there's also all these others, but for any one mass you pick, you can like find its like opposing, its enemy on the other side. So first I'm going to compare, so I'm going to say, well, one of them, is it pulling harder than the other? Or are they pulling equally? Well, let me compare their two masses. The two masses will differ only and exactly to the extent that the two surface areas differ, right? Like to the extent that the two volumes differ, but volume means surface area times thickness in the case of a shell, and the thickness is the same all around. So one of these masses is going to be bigger than the other only to the extent that one of the surface areas, one of like the swaths that we picked, is bigger than the other, right? Or I'm saying, that's what I'm saying so far. So the comparison of mass 1 to mass 2 is in direct proportion with, is the comparison of surface area 1 to surface area 2. And I want to go on to say, the surface area of a sphere, surface area of a sphere. Well, let's see, it's a sphere, so clearly pi is going to be involved, like circles. So pi is something, so is it like pi, what is it, like 4/3 pi r cubed or something? Oh no, cubed would be volume, right? So 4/3 pi r cubed, that's the volume of a sphere. We want surface area of, so we don't want r cubed. R cubed is 3-dimensional, that'd be volume. We know the pi was right because it's like a circle. So it's something like pi r squared. Is it pi r squared? Well, that's the area of a circle. Oh, it's not 4/3 pi r cubed. Oh yeah, the surface area of a sphere is 4 pi r squared. Oh, that's interesting. The volume of a sphere is 4/3 pi r cubed. The surface area is 4 pi r squared. It's almost like we took the derivative. Wait, 4/3 pi r cubed. It's almost like we took the 3 downstairs, multiplied the 3 by the 4/3, got 4. That's weird. Could that be a coincidence? That's probably a coincidence. Well, on the other hand, if you take the area of a circle, pi r squared, and you just bring that 2 down, you get 2 pi r circumference of a circle. That is so weird. That must be a coincidence. I'm sorry. What was I talking to myself? I'm sorry. What? Note what I'm saying here. I'm being a jerk anyway, but I am being serious. Like the surface area of a sphere, I'm reminding you, you may remember from the Euclidean backgrounds of your mind, the surface area of a sphere is 4 pi r squared. How do I remember that? I remember it as the derivative of volume. That is not a coincidence. We're going to see that. Ultimately, at first physics is about stuff moving through space and time. Ultimately, physics is about space and time, i.e. geometry. So, but right now I'm saying, I'm sort of foreshadowing that all of these weird squares and stuff are actually fitting together in some way. But I'm just remembering right now that the surface area of a sphere is 4 pi r squared. So here's what I'm really saying. And then I'll shut up for, I am watching the time and I know this is all, and I see there's something in the chat. But I'm saying the surface area of a sphere is 4 pi r squared. And remember, we just said that one of these masses will be bigger, will be more massive than the other to the extent that it has more surface area than the other. Right? The surface area is in direct, so we're saying mass is in direct proportion to surface area in this case. And surface area is in direct proportion to r squared. But F equals negative GMM over r squared. So what I'm just, this is an argument. We'll come back to this. You don't have to fully accept it at all. You need to accept the conclusion in order to do this problem. But you can let this sit, and we're going to see this from other perspectives. What I'm just trying to argue now is if you go back to this picture, like for any chunk of mass, if I'm inside a shell, right? What I want to argue is this whole shell is pulling. Like the shell is a sum total of lots and lots of dots of mass that are all pulling. Like, each one of them is pulling me toward it. But if I actually back up and think about it, like one random chunk that's pulling me toward it has a certain surface area, and I can find another chunk directly on the opposite side that has a surface area that's greater than the first one by a function of r squared. It would be like if it's 2 times as far away, its surface area will be 4 times as great, which means its mass will be 4 times as great as the first chunk. But it is 2 times away, and gravity says in the denominator that the farther away you are, the more that matters squared. So I'm being incoherent, but what I'm saying is, mass is in direct proportion to r squared. Force is in inverse proportion to r squared. Wherever you are in this shell, you can find a chunk of mass on one side pulling you one way, but it has a neighbor which is more massive by exactly the amount, that is more massive by an amount r squared, and therefore pulls stronger yet more weaker by an amount r squared. Therefore, it pulls the same. Therefore, wherever you are in the shell, any chunk that's pulling you one way, you can find a corresponding chunk that's pulling you the exact same amount in the opposite direction. So they all cancel out. That is what I'm trying to say. I'm going to pause for a second. I just want to sum that up. I'm going to look in the chat. Hold on 1 second. But that's it. And then I'm going to bring that back to the whole problem itself. But I'm saying. Okay. Hello? So I'm making a bit of a mess of this, but I'm saying, therefore, if you're outside a spherical shell, the whole shell pulls on you with a net effect equivalent to that of a point. located at the shell center. Like there is, if you're outside a shell, there is a gravitational effect, and it's equivalent to as though the shell were just a super dense point. If you're inside a shell, the net gravitational effect is zero, not because nothing's happening, but because everything's canceling itself out at all times, wherever you are in the shell. And then, again, to me, that's a little bit of a surprise. It's not obvious, but it sort of makes sense when I think about it this way. And it, by the way, it's also a little bit of a hint or a little suggestion as to why gravity has this weird expression in the first place of having an r squared in the denominator. What we're kind of saying here is that the force of gravity just emanates from things equally in all directions. It's not about what you do. It's just about you existing as a mass point. Any mass point that exists just pulls everywhere toward it in the same way in all directions. It's just a point pulling symmetrically through space in all directions. So any sphere of influence it has is like a sphere, like whatever a point of mass would do to something over here would be the same as what it would do to over here. And so the effects of gravity radiates out as though it were the surface area of some sphere, radiating out, like it radiates out as the surface area of a sphere. That's where the r squared is coming from, in a way, in that denominator. Now, why am I saying all this? To get back to the actual problem, to put these two results together. Oh, cool. Okay, yes, they cancel out, right? That's what's in the chapter. Okay. So now I'm saying I've got two cases. Okay, and now, by the way, I'm about to give you notes. We're gonna solve this problem in the exam, believe it or not, and then this will be your solutions for it if I don't post a different document. What we now have is two cases. We are saying, we believe now, I believe I've explained why it actually sort of makes sense that I can think of two, when there's a shell, I could be outside it and know that how it acts, or I could be inside it and know how it acts. Now for this, right, that's what this page says. For this problem in the exam, it's asking me in a way, well, it's asking me something that seems impossible to me. It's asking me what happens. Right, okay. It's asking me what happens here if my M2, my particle, is located at an independently variable displacement, lowercase r vector, from the center of a solid sphere. Okay, so now I'm going back to the question, the original question of what if we're in a solid sphere, like plum pudding, where the density is uniform throughout? Like, what can we say of this now? Again, this seems like, believe me, if it seems to you like an out of crazy left field question, yeah, even to me, even to Noon, there's a reason to ask it, but it seems like I don't even know how I would go about answering that. Like, what? But here's the deal. If we're inside a solid sphere, if we're somewhere random, like here, if we're at this random spot, if actually we think we know what goes on when we're outside a shell, and we think we know what's going on if we're inside, that's all that's happening here, but both at the same time. Like anywhere that we're in a solid sphere, what we're doing is we've got all this mass above our head, and we've got all this mass below our feet. In effect, anywhere we stand inside a solid sphere, we're standing on a small sub-interior planet. We can call it like the enclosed. So like I've tried to color it off in blue here. I know, like if I'm somewhere in the interior of Earth, like assume Earth is a solid sphere, like it doesn't have like mixy molten lava over here and rivers over there. Just assume it's like a big ball, and I'm somewhere displaced from the center, but not quite yet at the surface. I'm saying I can really think of it as I am trapped between a smaller subplanet, like I'm standing on top of an interior, right? Because there's all the distance between my feet and the center. So that's like I'm like the interior enclosed planet that I'm standing on. And then above my head is all this shell. Like they're both there, but I could consider a shell above my head and a planet below my feet. And I know how gravity works for each of those cases. What I can say is, oh yeah, all the stuff that's below my feet is just, I could just act like it's just all concentrated at the center. I could just do GMM over R squared on that one big chunk. And all the stuff above me all cancels out because it's just a shell, and I'm just in, right? As weird as this is, I'm saying if you're in solid, what you are really is trapped between a shell and a smaller solid. The shell all cancels out, we just argued. And all that's left is a smaller solid. So if I want to know, the entire gravitational effect of everything around me from somewhere, 2,000 leagues below the sea, and I want to know the whole gravitational effect of everything, the first insight is actually, as long as I know what's going on below my feet, that's all I need to know. Everything above my head cancels out. So the total gravity on me is just GMM over R squared, as long as by M, I mean the enclosed M below my feet. As long as I know what that is, then I have the total gravity on me, which is what the question's asking for. The question's asking, what's the total net gravitational for, okay? So bear with me, we're almost there now. We are past the hardest part. The hardest part was hard because it was like, why would we even want to listen? Like, what is he even talking about? But if you're still with me, if you got past that part, it'll start to make, I think, some sense now. I'm saying what I want to solve this problem. I'm just plugging in GMM over R squared. Only my M that I'm plugging in is the enclosed M, this fake, this blue planet, the fake, it's not a real planet. It's just it's a subsection of the larger planet. I'm saying that's only that mass is what's pulling on me. Whoa, I think something just happened. I hope not. So as long as I know what that mass is, I'll just plug that in and I'll have my answer. Now, what do I mean? What I know that mass is? As long as I know it as an expression, like expressed in terms of given knowns and constants. Like I know I was given the original mass of the whole thing, and I was given that the density is a constant. I just don't know like the mass where I'm standing on, the mass of the subplanet where I'm standing depends on where I'm standing. In other words, I'm saying this. Well, yeah, so I'm saying we just want an expression for M enclosed to plug into GMM over R squared. If I could just know what M enclosed is in terms as a function of known or given constants, that's my goal here, okay? And I'm watching the clock. This goal will be achieved before in time. I'm saying in other words, what is M enclosed? Well, it's some percentage of the total M. Like if I'm all the way out on the edge, it's 100% of the total M. If I'm like halfway, if I'm like at R, if I'm halfway between the center of all this and the edge, then I'm enclosing some portion of the whole thing. Am I enclosing half? Well, that's sort of what I'm trying to figure out right now. I would actually say I'm enclosing eighth. Here's what I'm saying. How could we do this? How could I express what the portion of total mass is that I'm standing on as a function of what I know? Well, remember, density is a constant. For any given chunk of volume, for any two equal chunks of volume, call this V for volume, we have two equal chunks of mass. Therefore, the mass per total volume, we'll use V for volume, the mass per total volume must be equal to the enclosed mass per enclosed volume. Enclosed is that blue inner region, right? If density is a constant, then the ratio of total, therefore I can solve, oh, here we go, therefore, so I'm saying this. Right? And I'm looking for M enclosed because as long as I know what that is, I'm going to plug that into GM over R squared and we'll actually be there. What's M total was what was given as, was called M1. Okay, that's fine. V total is the total volume of the whole sphere, the volume of the whole given sphere. I'm going to say, right, the volume of the sphere is 4/3 pi R cubed, and it's that given R because it's the given total sphere that I'm being asked for right here on this left-hand side of the equation. But then it says multiply by volume enclosed. What's that? Well, that is 4/3 pi R cubed. You see where I'm going with it? Okay, like that, where we're standing versus the whole thing. So now, so M enclosed equals, well, the things will cancel, like the 4/3 cancel, the pi cancels. And what we're saying is that M enclosed is equal to total M times R cubed over capital R cubed. Now that might, hopefully that makes a little sense when it's written that way. We're just saying like, look, if you're all the way at the end, then you're standing on 100% of the original planet. If you go halfway in and you stand at like a radius of half of the total radius, right? you're only standing on now like a smaller portion of the planet. You might think you're standing on a planet of half the volume of the original, but no, because space is three-dimensional. Like since volume goes as r cubed, if you're standing in half the radius, then the total volume that you're encompassing below your feet is 1/8 of the original volume, right? It's in the ratio of the cubes, because mass is in constant ratio to volume here. I can't like say it much, but so what's the point of this? So this is what I'm going to plug in back into the gravity. So I'm going to say, so again, it all seems like going round and round and round, but we're trying to use the gravitational expression that tells us what's going on between any 2 points. We're trying to apply it now to what's going on if we're immersed in a big solid. Like this is like a more advanced physics idea. And we're saying, we're going to plug in, and our big insight is, oh, all that's pulling on us ultimately is all the stuff below our feet. So if we knew that total mass given as an expressed as a function of things we know, then we'd be set. So that's what we're going to do. We're going to say, right? I'm plugging in the expression that we just got for M enclosed. That's why we did all that work, frankly. I'm plugging in this as M enclosed, and I'm arguing that is M enclosed based on uniform density. So now the lowercase r's are one and the same lowercase r. They cancel out. I mean, they sort of cancel out. So we get now we get this. We did all that work. And again, this is like, whoa, what? But we did all that to get this expression here. And we have 10 minutes. This is perfect, but I do need you to focus for these 10 minutes, which I appreciate you totally are, blah, blah, blah. I'm saying we just got this. This is the answer to part A of the problem. You might not even know what we've just done. Like the question was asking, what is the force as a function of R, function of displacement? Like, can you give us a force as a function of position? Does it sound familiar? We're looking for force as a function of position in part A of this complicated gravity situation that also we had to remind ourselves of how gravity worked in the first place. Then we got this crazy gravity situation, but it's not that crazy because it's just like what happens inside a planet. And what we're ultimately saying is, how gravity works inside a planet is like this. What we're saying right here, say quickly, we're saying that when you're inside the plum pudding, inside the solid, the force is directly proportional to displacement with a negative sign. In other words, here we're saying inside the Earth, if you're at r equals 0, you're weightless. There's no gravitation on you at all. As we predicted, if you're at the center, you're being pulled this way, you're being pulled that way, you're being pulled that way, all equally in the same direction. So you're pulled nowhere. But now if you start going out from the center, now in a solid sphere, if you start going out from the center, according to this expression, there will be a gravitational force. I'm not saying it all cancels out everywhere. We're in the solid sphere now. But according to this expression, as you get farther and farther away from the center, the pull gets greater and greater on you, but always pulling you toward the center. That's what that negative sign is. As you get farther from the center, the pull gets greater. So if you're halfway out to the edge of the Earth, according to this, you'll have a half of your surface weight. Gravitational constant for free fall won't be 9.8. It'll be like 4.9 is what we're saying. Like at our... Oh, sorry. Whoa. Okay, very quickly, and I am watching the time. What this is saying here is that inside the Earth, gravity is not inverse quadratic, it's linear. Inside the Earth, the farther you stand from the center, the stronger gravity pulls on you. So like if you were crawling from inside the Earth all the way to the surface and beyond, if you were plotting the force, it would look something like this. Like, I'm not sure if that diagram was worth it, but as you crawl out from the center of the Earth, the force gets stronger and stronger linearly until you get to the edge. And then as you get farther and farther, it drops off quadratically. Okay, why am I saying all this? Because bizarrely, as a result of that, as a result of the fact that this is the way gravity works on the inside of the Earth, we can then ask the next question, which would otherwise be an impossible question. We can ask the question of B in the exam. So this is where we're gonna, I know we have 7 minutes, but what's really weird is that we can even ask, let alone answer this question. And this is the question of B, is that if you picture now a whole big solid sphere like the Earth, and you carve a tunnel from one edge of the Earth, like all the way through the center to the other side, so like a big diameter tunnel, you drop a rock in one hole of that tunnel, one end of that tunnel, and just let it fall according to the gravity expression that we just got, just let it fall to the other side. We can ask, how much time would it take to get to the other side? And I know many of you have figured this out and some of you haven't, whatever, but I'm just going to say it now because there's limited time. We can figure this out, even though this seems like a really weird question, because what we're saying here is if you drop a rock into a tunnel, it's pulled by a lot of gravity right at the edge there, right at the surface of the Earth. But as it's falling, it's less and less of a force of gravity until it gets all the way to the center, where although it has a lot of speed, it doesn't have any acceleration on it anymore. It's not being pulled at all. But it has a lot of speed, so it'll keep going and it'll keep going, but have less and less speed while it gains more and more pull on it from being farther and farther from the center. Oh my God, what I'm saying is, as you may have already noticed, and if you did, that's awesome, and I would have made time for you to say it, but I can't. What I'm saying is, if you look at this expression, the reason we went through all this weird work, suddenly introducing gravity into the course and everything is, oh, in this application of gravity, the force is directly proportional to the displacement with a negative sign, or put another way, since F net equals still A, since F net still equals MA, right? If we're saying this, and R, capital R is just a constant, right? Oops, sorry. So we're saying this. And the negative sign means being pulled toward the center. We're saying this now, but remember, right? So what we have here is a harmonic oscillator, right? But like, whoa, like we're saying a tunnel with nothing in it but gravity, but a vacuum. Like gravity will act like a spring here. Gravity will pull harder and harder as you get farther and farther away from the center. It'll pull less and less as you get closer to the center, exactly linearly, just like a Hooke's law spring. So that as you fall to the center, you'll gain kinetic energy, but you'll lose potential energy, all the things. And if you were to fall all the way to one side, you would then fall back to the other and swing back and forth with an angular frequency, which would be the square root of this constant here, right? So thus M2 will oscillate gravitationally, at an angular frequency of square root of GM over R cubed, which means therefore that the frequency would be that divided by 2 pi, which means that the period would be 2 pi times the square root of GM over R. This is how you do it, okay? So that means that literally if you have values for any of those, say you're talking about the Earth, if it's the Earth and it's 127, so what we're literally saying here is, if you want to know how much time it would take for something to go all the way across to the other Earth, well, that would just be one full cycle, but that would be one half of a cycle there, but not come back, right? And that would literally be and if you plug in the value, I'm just saying this quickly now, you can test this at home when you, but I'm literally saying here, oh, what we've just shown is that inside a solid sphere, gravity acts like a spring. It produces harmonic oscillation. And the amount of time for one trip across this oscillating tunnel would be like a period, would be the amount of time for, in this case, half of a cycle. Period is the inverse of angular frequency. The angular frequency is the square root of the constant of proportionality. If you plug in the numbers, what you will find, and you can test me, is that if you drop a rock and if you carved a tunnel all the way through the center of the Earth, all the way to the other side, and just carved it out so there's nothing, no friction, no dirt, but nothing but gravity. You drop a rock on one side. Number one, what I'm saying to you all right now is it'll land on the other side in 42 minutes. Like, you can work out the numbers, you can plug them in, assuming Earth's radius, Earth's math. To get to the other side, it'll be 42 minutes. Okay, that's and we know that even though it's constantly changing its acceleration, it's constantly changing its velocity, but it's doing so in a harmonic oscillating way. So we figure it out with our harmonic oscillating methods. With one more minute left, let me just tell you that the only other thing that's asked on the exam, and this is mind blowing, and I probably won't ask it on yours because it's a bit much, but I'll put a diagram in the posted solutions and everything. The last question is like, what if you carved a tunnel that wasn't through the center of the Earth? Like, now, in other words, a much more realistic, like, we can't go through the center of the Earth. Like, it's like hell down there. But what if you just dug an arbitrary chord, a tunnel from one edge of the Earth's surface, and I am watching the time, to any other place on the Earth's surface? Like, not a tunnel through the center, but just like a tunnel from Brooklyn to London, or Brooklyn to Queens, or Manhattan, right? Just a tunnel, right? I'll put a diagram in your solution so that you can see what I'm about to say. The coolest thing is this: if you put a realistic, everyday, short tunnel of arbitrary length, one that didn't go through the center of the Earth, it can be easily shown in one diagram that would be an oscillator of different size from a diameter tunnel, but of same angular frequency. That is, any tunnel you dig through the whole Earth, all different tunnels of different sizes, are all different amplitudes on the same one gravitational oscillator that has an angular frequency of this R cubed over GM square root thing. No matter what tunnel you pick, it's a different amplitude, but it's of the same oscillator, the same K over M, whatever you want to call it, same omega. Therefore, any tunnel you pick, even realistic tunnel from Brooklyn to Queens, if you literally carve it out, get rid of the frictional effects, the fire and brimstone, and just drop a rock or a person or something you need transported, and just let gravity do its thing from one edge of any tunnel to the other of any size, according to this reasoning, it would be 42 minutes. Longer tunnels will be longer, but the object will have more potential energy and therefore on average more kinetic energy and do them faster. Shorter tunnels will be shorter, but objects will do them, and it will always be 42 minutes. That's a fact, yo. The gravitational tunnel of any size, because it's a harmonic oscillator, is 42 minutes. Okay, but I know I totally went over time. It's community hour, whatever that means. I will post like updates and this and that. Remember, your exam, as hard as this may be, your exam can only be as hard as this, no harder, if that makes sense. And it'll probably be pared down a bit. I will watch for notifications and stuff in the Google Classroom until then, but I think it's time to go. So goodbye. Thank you very much. Okay. Thank you. Awesome. Thank you. Have a nice day. Bye. Thank you. Have a nice day. Bye.
Bye, Professor. Thank you.
Bye. Thank you. Awesome. Bye. Thank you. Bye. Thank you. Bye. Okay. And Eileen and Heaven, you guys are good or? Okay. Oh, let me just see the channel. That's all. Okay. Right. No, Justin and Alyssa, great. Wait, let's talk for a second. Well, I think, oh, actually, you know what we can even do? Here's a weird thing. I know this is strange, but let's just put ourselves in a breakout room here. Hold on a second. What? Okay. Okay. Now how do I? Sorry. How do I join though? Wait, sorry. How do I actually join? What? Wait. Wait. Hi. Okay. Sorry. Hello? Are you good? Oh, wait. Sorry. Oh, hi. Okay. Guys. Oh, sorry. Are you guys there?
Just you get like a few controls, but I don't think it allows you to. I mean, maybe it does because I've seen like the people that do like the raids and the zooms, and you know you have to take people out and that.
Hi. Speak. Can you guys hear me or no? Am I in your room? Oh, okay. Cool. Because I didn't even know how to join. This is weird. Sorry. And am I so? No, I'm glad we're meeting. And thank you for making this time. And let's do this. But wait, I'm weird. Hold on. I'm going to actually let this breakout room thing is weird because I'm in two devices at once. I know what to do.